Ever wonder how AI actually understands language? Not just the theory, but the real nuts and bolts? Today, we are cracking open the engine that powers modern AI attention mechanisms. This isn't abstract theory. This is the code, the implementation, the actual machinery that makes language models work. By the end, you'll understand exactly how to build these systems from scratch. Think about how you read a complex document. You don't give equal focus to every word, right? Your brain automatically highlights what matters and dims what doesn't. That's essentially what attention mechanisms do for AI. They're the brain's spotlight. First, we calculate attention scores, essentially measuring relationships between every element in our input. We use the dot product between word representations, which gives us a mathematical measure of how related any two words are. It's elegant and computationally efficient. These raw scores then go through a softmax function, transforming them into a probability distribution. What emerges are attention weights. The higher the weight, the more focus that element receives. Now comes the magic. We use these weights to create a context vector through a weighted sum. Imagine highlighting parts of a sentence with different intensities based on relevance. That's what this vector captures, the essence of what matters most. But here's where it gets interesting. With generative AI, we need to prevent the model from picking ahead when generating text. That's where causal masking comes in. Picture putting blinders on the model so it can only see what came before. Technically, we set future attention scores to negative infinity, which zeroes them out after softmax. The model physically cannot attend to words it hasn't generated yet. That's how we maintain the integrity of the generation process. Let's go deeper. Single attention is powerful, but multi-head attention is revolutionary. Instead of one perspective, we get many, each head learning different relationship patterns simultaneously. It's like having multiple experts examining the same text from different angles. One might focus on syntax, another on semantics, another on entity relationships. Each head has its own weight matrices, learning different patterns during training. When combined, they give us a richer, more nuanced understanding. But wait, how does the model know word order? Attention itself doesn't care about sequence. That's why we add positional embeddings, special vectors that encode each word's position. Without this, dog bites man and man bites dog would look identical to the model. These embeddings can be fixed mathematical functions or learned during training. They are added directly to word representations, giving the model that crucial sense of sequence. So, why should engineers deeply understand these mechanisms? First, for better design. When you understand attention, you can make informed architecture decisions, how many heads to use, embedding dimensions, positional encoding strategies. Second, for debugging. When your model fails, attention weights give you a window into its decision making process. You can literally see what your model is focusing on. Third, for optimization. Understanding attention lets you implement efficiency techniques like sparse attention or kernel fusion, making models faster and more memory efficient. The power of attention can't be overstated. It's the foundation of every breakthrough in language AI over the past 5 years. It's what enables these models to write essays, generate code, and have conversations that seem almost human. And we are just getting started. The next breakthroughs will come from people who deeply understand these mechanisms and can reimagine them. Could we develop new attention patterns, new masking strategies, new positional encodings? This isn't just academic, this is the cutting edge of AI. Master attention mechanisms, and you're not just using AI, you're building its future.